In this video, we kind of step away from the series tests. Not that we're done with them, we're going to still use them, but we're going to start applying these series to some kind of slightly different concepts. Okay, we're going to take this kind of back and start talking about then functions and derivatives and antiderivatives again, but all in the context of power series, right? We're leading up to something kind of big. But what I want to talk about in this video is what a power series is, and it's not too much different than what you're familiar with this series already, and you know what it does and when they converge and when they diverge. So I'm still asking really the same basic questions. We'll have some new definitions here, but for the most part, we'll just take things a little slow. Take your regular geometric series. Your regular geometric series is sum from 1 to infinity of AR to the power n. We know the convergence of this guy converges when the common ratio R is less than 1 and diverges when the common ratio is bigger than or equal to 1. Okay? So we're going to use that a lot in this video. Let's take and consider if R is X. So really, it seems like we're just kind of switching letters here. My power series is now, or I'm sorry, I gave it away. My geometric series is now A times X to the N. So my common ratio in this case is X. That X we're taking to be a variable instead of kind of a fixed number as we were before. Before we would say, oh, R is a half, R is 2/3, and that was a fixed common ratio. Here, we're kind of letting that common ratio free a little bit. We're letting it be a variable. We're letting it kind of change. We can still talk about convergence and divergence. In fact, it's still a large topic. This guy still has convergence when that common ratio, in this case then X, is less than 1, and divergence when the common ratio is, of course, greater than or equal to 1. This guy, as I mentioned, is called a power series. It's called a power series because what I've got is powers of X added together over and over and over and over again. It's almost like an infinitely long polynomial, right? So what we'll be looking at is when these power series converge and diverge. More generally, here what we have, the general formula for a power series is the sum from 0 to infinity of a sub n times x minus c to the power n. And if I go out some terms, when n is 0, we see the following thing. A0 plus, when n is 1, I start seeing this x minus c show up. And if I keep going, I keep seeing more and more powers of that x minus c. This is a power series, and we say that it's centered at x equals c. Okay? So we can think about a series centered kind of wherever we like. A lot of times we'll focus around the origin, having a center at 0. But we do, want the possibility to be able to move a power series around. So the center is a general thing. And what I want to do is lay out when these power series converge. And what I want to say first is that this a sub n here, these a's, could give us all kinds of interesting things. Okay, there could be n's involved in those a sub n's, right? They could just be a constant number all the time. They could just be 2 for every a, right? But it could also depend on the term that I'm at, right? It could depend on n. And that might change the convergence, okay? So not all of these are exactly geometric, though I want to kind of think about things kind of starting that way because I think it helps how you come up with the convergence. So let's look at this general power series here. This is theorem 9.20. You don't have to remember that theorem number, but what we're going to be working with here is the convergence of a power series. There are 3 potential outcomes. The first is that the series converges only at its center. In fact, the series will always converge at its center. It might converge at more numbers than that. So this is kind of always a fallback. So it's always going to converge at the center, but maybe that's the only place that the power series converges. It happens. Okay, this is not necessarily a boring case, but it's the one that's always there, basically. Second is the slightly more interesting. The series converges absolutely on some interval for some x's that are the distance between x and c is less than r. Okay, or we can kind of expand this to write, we can open up our absolute value and say that c minus r is less than x is less than c plus r, where r is bigger than 0. This r here, and the series then diverges for everything else, right? When x minus c is bigger than r, okay? What does this look like? Here, this r, we actually have a term for r. R is called the radius of convergence. And I want to draw this on a number line for us because I think it's a little bit easier to see. So we have some center, I'm going a little fast. We have some center of our power series. And then to the left and the right of this center, we have kind of endpoints. Those are the endpoints of our interval of convergence, right? The kind of outer radius, the furthest places where our power series converges. So what can happen is that for any x within this interval, for any x that's within the r of the center C, we have convergence. So we're going to converge all in here. Okay? This is what this second option kind of says. And we're then going to diverge everywhere else. Now, these distances there, that's our radius of convergence, right? That's our r. And we diverge everywhere else, okay? I think this is kind of a helpful thing to see visually what's going on. We'll do some examples where I actually see numbers where C and R are, right? We'll have a center and we'll have some actual radius that we can work with. But in general, this is the kind of the most, I guess, common possibility, a possibility where we're seeing, that our power series is only converging in some small window around the center. The third option is the one that we actually want. I'll explain this a little bit later in some further videos, but what we want here is actually for a power series to converge for all x. And what that looks like is it's just convergent everywhere. Okay, that's what we want. And in this case, our radius is actually infinite. The radius of convergence is infinite. We converge for all x. And if I can direct your attention back to number 1 here, we actually have a radius of convergence when the power series only converges at the center of 0. The only place that I converge is at the center. There's no radius of convergence. Okay. So in the next couple examples here, I'll be talking about this, what we call the interval of convergence. This x minus c is less than r in absolute value, and the radius of convergence and how we determine those things. So I'll be kind of alluding back to this theorem as I go. The first couple examples I want to look at are geometric series. Okay, not all of them will be geometric, but some of them will, and they're easy, because we know the convergence of geometric series already. If I go back to our kind of most general example, notice that my a sub n here is just kind of a hidden 1. There's not some extra constants that are coming into play here. This is just the power series from 0 to infinity of x to the n. So I'm adding powers of x to one another. This guy has convergence. This guy, well, first, let's pick out the center. Center, we're looking for an x minus c. And we'll notice very quickly that I don't see an x minus anything. So that I can say then that the center is, of course, 0. This guy has convergence for the x there, this geometric, right? So it's a common ratio. X is less than 1 in absolute value. That 1 is also my radius of convergence, okay? What this means is I have an interval of convergence. The interval of convergence is the x's for all, or for which this power series converges. And that's just the same as this guy up here for x between minus 1 and 1. That's what it means for the absolute value of x to be less than 1, right? Is that x is between minus 1 and 1. I also have a radius of convergence. The radius of convergence is 1. Okay, so again, just quickly on a number line, all this looks like, right, is I have a center at 0 and a radius of convergence of 1 in either direction. This is the place where my series is going to converge, all in here, and diverge everywhere else. Okay, so this is again kind of option 2. I didn't choose this option. I say option. I didn't choose this option, but that's the outcome that we're kind of stuck with. We have some specific interval and radius of convergence here. Okay. Another example. Let's look at number 2. The power series x minus 2 to the power n. If I write out some terms, that x minus 2 I'm going to start seeing powers of as I go. Okay. Now again, this is geometric, right? I take this common ratio, x minus 2, and I can see my center there, x minus c is x minus 2, so center should be 2. And I can see that the interval of convergence is going to come when that common ratio, x minus 2 in absolute value, is less than 1. I'm going to take this apart a little bit, right? Open the absolute value. And what I get is minus 1 is less than, x minus 2 is less than 1. Add 2 to both sides, and I see that 1 is less than x is less than 3. This is my interval of convergence, okay? This is my interval of convergence, and I typically write that the interval, x is included in the interval from 1 to 3. My interval of convergence is just that. Okay, those are the places where my series converges. The radius of convergence is again that 1 on the right hand side. Radius of convergence is 1. And again, just quickly, number line. My center, this series was centered at 2 with a radius of convergence of 1. So again, on either side of 2, I go out 1 unit. And as long as my x's are within this window, we say that the power series converges. So again, this series is going to converge as long as x is within this window and diverge then everywhere else. Diverge everywhere else. Okay. Another quick example I want to do where the radius of convergence isn't 1, because it's getting boring. I take this series here, the sum from n equals 0 to infinity, of x plus 2 divided by 3 all to the power n. Okay? And I'm writing this kind of as it looks like a geometric series, because then I can just quickly extract this common ratio. And what I want to write this as is so I can see the center, right? So what I do is instead of x plus 2, I write that as x minus a minus, right? Because I want to see x minus c. The formula is x minus c, not x plus c. So the center here then I can say is negative 2. And the radius or the interval of convergence I'm going to come up with as long as that common ratio is less than 1 in absolute value. And I'm going to start taking this apart. The 3 in the denominator, the 1/3 I have, I'm going to bring out front. And then I have x minus a negative 2 again. As long as this is less than 1, I have a convergent series. I'm going to multiply both sides by 3. That 3, the absolute value, has no effect on that 1/3, right? So multiply both sides by 3. And what I get is my radius and interval of convergence looking at me right here. Okay? So again, I have a center at negative 2. As long as x minus c is less than r in absolute value. R then is this 3. My radius is 3. The center is minus 2. And I just write those out. Radius of convergence is 3. The interval of convergence then is 3 units on either side of negative 2. So I take my interval there, starting at negative 2, and I go 3 units to the left and 3 units to the right. And that puts me here, basically. Again, I open the absolute value. Negative 1 is less than x plus 2 is less than 3. Subtract 2 from both sides. I get minus 5 is less than x is less than 1. So my interval of convergence is from minus 5 to 1. Okay, and again, I can quickly put that on a number line pretty easily and see that I go 3 units in either direction away from my center. If I can draw here, here's my center at negative 2. I have then a radius of convergence of 3 units in either direction. So that brings me to a negative 5 and a positive 1. And for any x within that window, I am going to converge. I think you get the idea. And then diverge outside of this window. Right? Oh, I drew it down here. There you have it twice. You're welcome. Okay, now, of course, not all power series have the same shape as a geometric series. We have to be able to dissect these for any type of power series we have. I need to be able to find the radius and interval of convergence because that's where these series converge, right? I want to talk about them when they converge and really not any other time. So we need a way to come up with when a series converges if it's not a geometric power series. So what I want to do is find the interval and radius of convergence of this power series here. So this is a little bit different looking. I have n factorial times x to the n. Now this n factorial is like that a sub n. It depends on n. Those are the coefficients of my power series. So what I will do here is we're going to use the ratio test. We're going to use the ratio test because that's going to give us absolute convergence, and it will kind of basically, by default, give us an interval of convergence. And I'll show you how that works. But if x were to be a number there, say 2 to the n factorial times 2 to the n, you would do ratio test on that anyway. So regardless what x is, you would still use the ratio test to try to come up with convergence or divergence. We're just now going to have general x's involved. So when I set up my limit here, this is the limit of absolute value of, in the numerator, I have the n plus 1 term is n plus 1 factorial times x to the power n plus 1. This is divided by the nth term, just n factorial times x to the n. So I'm going to split things apart, of course, and there's going to be some cancellations going on. I can pull off my factorial here, have an n plus 1 times n factorial, and an x to the n plus 1. I'm going to pull off an x and have x to the n there left over. I see these cancellations, right? N factorials cancel, x to the n's cancel, and I'm left with n plus 1 in absolute value times x. Okay, this is the important bit. Because what happens here is I'm taking a limit as n goes to infinity. X has nothing to do with n. X is considered to be a constant in terms of n. So what I'm able to do is take this x out front and write it in absolute value. Right? I can't just pull it away for free. It's still absolute value of those x's. X has a potential to be negative, so I need to keep those absolute values there. But the absolute value around n plus 1, I can get rid of because n's are positive, so n plus 1's are also positive. Okay, so I have the limit then, as n goes to infinity, of n plus 1 times the absolute value of x. This limit is infinite, right? Because as n gets bigger, the limit is going off to infinity unless that x out front is already 0. If x is not 0, this limit is infinite, okay? But if x was already set to be 0, I would just be summing up a bunch of zeros. Remember that a power series always converges at its center, right, from our theorem. This is that situation where I have a center of 0, right? I didn't make mention of that before, but this is really case 1 of theorem 9.20, my power series converges at its center. However, series always converge at its center, and in this case the center is 0. So the interval of convergence is just x equals 0, and the radius of convergence is nothing, 0. Okay? So it might seem like a silly example. The only place that this series converges is when x is 0. But it's an interesting thing. Right? It's an interesting thing, and this is the first kind of time that we have a test to find this interval of convergence. I'm going to do another example where I apply the ratio test, and I'll go through it a little quickly to find the radius and interval of convergence, hopefully dealing with a slightly different example here. I have the sum from n equals 0 to infinity of x to the n divided by n factorial. Again, same question, find the radius and interval of convergence. I'm going to apply my ratio test, set up my limit. For every x, for every n, I replace with n plus 1. And remember, I divide by the nth term. We almost always do this reciprocal action, right? So the nth term is x to the n divided by n factorial. I want the reciprocal of that. I see n factorial divided by x to the n. Again, split some things apart. I see some cancellations coming. With n going to infinity, I have x times x to the n divided by x to the n. X to the n's are going to cancel. I'm left with just an x in the numerator. And n factorials are going to cancel, leaving me with an n plus 1 in the denominator. Okay, so this is an interesting example. Oops, sorry, went a little ahead. I've got cancellations kind of all over the place. Again, I have absolute value of x in there. I can pull that outside the limit because x does not depend on n. So I see absolute value of x out front times the limit. And again, these n's are positive. So I can drop absolute value. I'm taking the limit of 1 over n plus 1. That limit right there is, of course, 0. So I take absolute value of x and multiply it by 0. Now, what does the ratio test tell me? It tells me that as long as this limit is less than 1, the series converges, right? So this guy is 0, which is indeed less than 1. Okay? Absolute value of x times 0, don't matter what x is, as long as I multiply it by 0, I'm going to get 0. By the ratio test, as long as this limit is less than 1, as long as the entire limit, right, this whole thing is less than 1, I have a convergent series. The limit that I got is 0, which is always less than 1. So what we've got here is we say that this power series, this series, converges really for any x or for all x. Because it doesn't matter what this x is out front, it's being multiplied by 0, and that way this limit is always less than 1. Okay? So the interval of convergence is really everything. Converges for all x. It's from minus infinity to infinity. And that also implies the radius of convergence is infinite. Cool. Again, this is the situation that we want. This is case number 3 from our theorem, where we converge for all x. And like I said, you'll see why we want this to be true. Why we want this to be true for the series that we're working with is converging for all x. I'll do some more of this in another video. But another quick example here to illustrate something that we have to pay attention to. Again, I want to find the interval and radius of convergence of a similar power series here. I've just taken away the factorial in the denominator. Something interesting happens here, and I want to talk about it. So again, I'm going to apply the ratio test again rather quickly. The series looks like this guy. When I use my ratio test, I see I get some cancellations again, but only x to the n cancels. I'm left with an x out front here and an n over n plus 1. Again, I can take out this x in absolute value, and n divided by n plus 1 is positive for sure. Okay, so I see this, absolute value of x times the limit as n goes to infinity of n over n plus 1. Now again, this whole limit, if this whole limit, the entire thing, not what I've underlined there in yellow, but that whole thing, if that whole limit is less than 1, I have convergence. Okay, I can evaluate the underlined limit in yellow separately, right? So the limit as n goes to infinity of n over n plus 1, that limit is 1. So I have absolute value of x times 1 is less than 1. That whole thing is less than 1. Well, when is it less than 1? That's kind of what I have to find out. What this has given me is really an interval of convergence. This tells me that as long as absolute value of x is less than 1, the limit that I've taken is less than 1. Does that make sense? I'm using the ratio test. The entire limit has to be less than 1. As long as absolute value of x is less than 1, I have that limit being less than 1. This 1 there, that's my radius of convergence. So for a series centered at 0, my radius of convergence being 1, I've got an interval that looks like this. My series converges from minus 1 to 1, which means my interval of convergence is from minus 1 to 1. X is between minus 1 and 1. Of course, the radius of convergence is 1, but what's going on? What about these endpoints? I didn't make much mention of it before. What about minus 1 and 1? When we were dealing with just geometric series, we never converge at the endpoints, right? And I didn't say much about that, but it's true because if I were to plug in like the endpoint to my geometric series, I'm just going to be adding minus 1 or 1 together forever, or alternating. But there's a chance that a general power series can converge at the endpoints. So in general, we have to check these every time. Let's check to see if these endpoints show convergence or not. And what we're going to do is actually just plug in the endpoints. When x is 1, my power series is 1 to the n over n. Right, I'm literally taking x is 1 and plugging it into my power series. Okay? This guy is exactly just the sum from 1 to infinity of 1 over n, which is the harmonic series. We know this diverges. So when x is 1, we have diverging at that endpoint. Okay, that's going to affect that endpoint there on my number line. Let's check when x is minus 1. We get a slightly different series to work with here. Minus 1 to the n over n. This is one of the examples we did in 9.5 dealing with alternating series. If you apply the alternating series test here, you will find that this series converges. Converges by the alternating series test. So what we've got is we've got one endpoint where the power series converges and one where it diverges. That's going to change our interval of convergence. Okay, so the interval of convergence for the original power series we were working with is now this. It's what I think about as a new interval of convergence. It's then from minus 1 to 1, but I'm able to include minus 1, and I can't include 1. So inclusive now, I'm able to put a bracket around minus 1. This is what it means really to have an interval of convergence. We always have to check the endpoints to see if we have a converging or diverging endpoint. And it just depends on what you've got. I'm only going to do one example here, and that's this one. I'll let you kind of look through some other examples and things like that. But you might go through an example and see that the answer has one of the endpoints where you're converging and the other where you're not. That's because of this kind of test, right? You have to plug in those endpoints and see what kind of leftover series you have. You might apply some other test. It might be easy, it might be difficult. You might have just a harmonic series that you can tell right away. I didn't go through the criteria for this alternating series test, but it's something we've seen before. So you can do that on your own. In general, power series have an interval and radius of convergence, and you might have endpoint convergence. That's something that you have to check. I'll do another, hopefully short, video from these two sections, 9.8, 9.9. This is an introduction and kind of a run through of radius and interval of convergence. And next, I want to take a look at maybe some rational functions as power series, and also take a look at some derivatives and antiderivatives. Thanks for watching.